Hello everybody, and my name is Jakob Wassermann. I'm from University of Applied Science, Technikum Wien in Austria, and I present a common work that we did with uh, AGH, University of Science and Technology, according to automatic classification of full thickness macular hole in optical coherent tomography. Um, Okay. The outline of my presentation is following. I will start with small introduction. Uh, then we will talk about description of this disease and and how this disease could be detected. It could be detected by optical coherent tomography. And then we will talk about image analysis. Um, so how we can automatically uh, detect this disease, and especially about generation of contours and angulation, and on the end conclusion. We will start with eye anatomy. I think most of you know uh, how our eyes is built. Here we have a retina, and this small part is called macula, and this part is very important for our vision because it's defined our sharpness, and also it contains sensitive rods. It means it is responsible for our color viewing. And what can happen? Oops, that this macula uh, is disturbed. It has a so-called a hole. This is this kind of disorder, uh, and this causes, of course, a lot of problems for the people. They cannot see sharply, and they have a difficulties in day life. Uh, Mostly people of between 60 and 90 years uh, are at risk with this disease. And but the good news is by a surgery, it is possible to repair uh, to repair this, and actually uh, it has a high success rate. So the main problem will be how we can uh, detect this illness. Um, this can be done by optical coherent tomography. So what we see here is a scan of a normal retina. So this is what we see here, and this is a macula. So it's a healthy macula. So what we have in our case, and um, now we will see some pathological cases. So here we have a disruption, and also here we have disruption of and here. So it means our macula has now got a hole, and um, what our purpose is to detect automatically this kind of disorder, and then uh, to to give a correct diagnosis to the patient. Yes, and by the way, if this is detected, this macular hole after the operation, we have this situation. So this is disrupted macula, and after operation, it looks better, and it can improve massively uh, the capability, vision capability of a person. Oops. So what is here? Sorry, I have here. Now I can go to present mode again to. F5. Okay, so this is okay. So, so, so the main approach to detect this disease is, of course, image analysis, and of course, machine learning and is uh, could could or should be the first choice, but we have here a small problem because we don't have enough training data. And for this purpose, we choose another approach by not by machine learning, by applying image processing techniques. Uh, and it's also possible by this method to address also a greater number of these disease characteristic. uh, so, what is our proposal? So, for detection this macular hole, this full thickness macular hole. Um, so we are converting our image into contours, separation of contours of the upper edge of the retina. Then we are detecting sudden change in the gradient, and we also can detect so-called retraction effect. And then we can measure distance between upper edge of a retina and retina pigment epithelium. This is a important layer that I will talk later about this. So this is example of contour extraction. So you see here this our pathological case. So we have a hole here, this uh, macular hole, and by applying some uh, algorithm for contour generation, we can retrieve uh, this one contour. And now, so this separation of these contours is, of course, several procedures. First of all, we are applying KNH detector to enhance the most interesting areas. And then we the resulting, we're converting it to binary image, and this binary image is undergoing such a single step parallel contour extraction. Uh, then the detected edges are presented as one pixel thick contour. It means that the contour should not be thick, it should have a thickness of 1 pixel. Um, and we are taking the first contour from the top. Um, then we can detect sudden change in the gradient. It's can be, I can explain it better here. So we see this is our contour, and if we calculate the gradient of this contour, it will be also less constant. And then here on this point, we have suddenly a change, and this could be calculated or could be detected, and this could be a sign that we had a pathological case. Uh, this third algorithm that we are applying is so-called retraction effect of upper edge retina. So I mean, we can see it here. After we detected uh, a gradient, we can see we can follow, we can trace this retraction. It means it goes in other direction, and this is also a sign for us that we have here a pathological case. And the last algorithm that we apply, we're measuring the distance between macular hole, this is our macular hole, and so-called retinal pigment epithelium. It is this layer. And this distance is very important So if this distance is too short, so then we have also a pathological case. So uh, yeah, so how we can uh, calculate this distance? For this, we need first of all, um, so this is our retina, and we should bring it in a horizontal position just uh, by turning it. Uh, by turning it, we bring it in a horizontal position, and after this we are doing some segmentation, and after segmentation, we are generating contours. Uh, yes, and in this generated contour generated image, it is easier to calculate this distance. Before we need to uh, define where this RTE layer is. Yes, and then to classify to classify the images, we created a metric, uh, so-called accuracy (ACE), that determines the probability of correct prediction, and therefore is defined as followed. So TP is true positive, FP is false positive, NT is true negative, and FN is false negative. Um, yes, what is true uh, uh, negative rate? So it is actually um, if a healthy person, it's a probability that the test will not detect the disease for a healthy person. So we know it actually from Corona, it's some similar nomination was. And so we used so true positive rate is a rate. Uh, a sick person will show that he or she is really sick. So this is true positive and this is true negative. Yes, and this is our result. So this is ACC classification accuracy is very high, 0.9877. Uh, true negative rate is also very good, 0.989, and true positive is 0.881. Okay, so, whoops, yes, I did some mistake. Conclusion. Uh, as a result of carried out experiment reported above, show that proposal approach is very promising and is superior to other solution of this type. So it means with our method, we can detect more precisely this disease, that method that exists now. And the reason for this is because we can address more pathological features and detect them than, for example, could be done with machine learning. Yes, thank you for your attention. After